The second video, geometries, is all about, is something polar or not? So the question first is, do you have a polar bond? Very straightforward. We just have to refer back to that electronegativity value table that we learned about in our Lewis structure video. So I'll show that again just in case if you don't have it. And then from there, we'll use those values and our bonds, being polar or not polar, and figure out if our overall molecule is polar or not. On your screen now is the electronegativity value chart that I just referred to and that you should have seen in the Lewis structure video if you had watched it. So here you can go ahead and pause and take a screenshot if you don't have this resource already at your hands, but we're going to refer back to it as we need to figure out every single bond if it's polar or not, which is a really simple calculation of just subtracting two different numbers. So let's go ahead and get started. Okay, so these are the two geometries that we went over in the geometry video. And so we're going to go ahead and move on with them. So in both of these examples, we never gave a true element to any of this. So let's go ahead and start there first, and then we'll move on. So starting with trigonal planar, let's go ahead and say BF3 is the example here, because BF3 is trigonal planar. As you can see here, I went ahead and redrew the trigonal planar geometry, actually substituting in where the boron and the fluorines should be. So the next step that we need to do is look at our electronegativity values and actually write down what the electronegativity is for boron and fluorine. So looking those up, boron has a value of 2.0 and every single fluorine has a value of 4.0. So anything that is greater than or equal to 0.4, when you do the difference between the two atoms that are involved in the bond, we can say that we have some type of polarity. Now, going from 0.4 to 1.7 is normally an indication of having a polar covalent bond. Covalent, as we should know at this point, means that two electrons are being shared within a bond. When you have something that's polar covalent, you have an unequal sharing. And so the story I like to say to my high schoolers is, if you and a friend were to go get some French fries and be sharing them, and your friend starts eating way more than you, that's unequal sharing. So the same thing goes for a polar covalent bond. So anyway, once you reach over 1.7 for the difference, which we technically have here, and you'll see that in a moment, you actually become more of an ionic bond. But in this case, let's go ahead and just follow through with how you would go about if you had a polar covalent bond. So what we need to go ahead and do is take the difference between 4.0 and 2.0. For every single one of those bonds, the difference should be 2. But let's go ahead and write that down. So at the bottom, you can now see the math that you have to do. If for some reason you accidentally did 2 minus 4 and got a -2, that's fine. Just do the absolute value of it. It really is just the difference between the two and whatever the positive value is. When we go ahead and draw a vector in, it's showing us that we have a polar bond, which we have in every single case here. What we want to go ahead and do is direct the vector from the more positive charge to the more negative charge. We can also denote this as a partial positive and partial negative charge, or we also can refer to it as which one is relatively more positive and relatively more negative. So, in order to be able to figure this out, it's quite simple. Whatever one of the electronegativities is higher, that's your negative one. And whichever one has a lower electronegativity value, that one's your positive. So when 4 versus 2, 4 is greater, so that would be our negative, and 2 would be our positive. Now all of our vectors are heading out, and so to be able to see what's going on, we actually have to figure out, are these going to cancel, yes or no? So I like to think about, if every single vector is heading out, you have to think about like a tug-of-war type of situation. And so if I go ahead and put my planar, trigonal planar geometry out there. We know that this is all laying flat on that piece of paper, and every single arrow is heading out towards the white spheres, okay? And we also should know that everything is equally spaced. And so since everything is equally spaced and they're pulling in opposite directions, there will be no movement of this silver sphere in the middle here. If there's no movement, it means it's non-polar. Then you do have a polar molecule. However, in this case, they're all the same, and they're all pulling in opposite directions. So we have a non-polar molecule. And so I made a note here on the left saying that, yes, we have polar bonds, but no, we do not have a polar molecule. Another thing to note before we move on to a tetrahedral is that if you ever have no for your answer of polar bonds, then there's no way you can have a polar molecule. So let's go ahead and do an example of a tetrahedral. Moving on with tetrahedral, our example is going to be CH4. And as you can see, I actually plugged in where the carbon and the hydrogen should be. As we did with the last one, we need to figure out what our electronegativity values are and do the math that we have at the bottom of the screen for our last example. Okay, so we went ahead and plugged in all the electronegativity values for both hydrogen and carbon in every single respective place. And I'm showing the math here at the bottom to show the difference. So carbon's 2.5 and every single hydrogen is 2.1. And so the difference between the two is 0.4, which is super borderline. However, as we denoted before, if it's greater than or equal to 0.4, we're going to call this polar covalent. And so that's what's denoted at the bottom here. We then have to go ahead and do our vectors just like we did the last time. And we want to denote which one is the partial positive and partial negative. Remember that the one, or the electronegativity, should I say, that is greater would be the negative of the two. And so in this case, carbon's going to be negative. And just note, in another example, carbon could be positive. It just depends on what it's bonded to. And in this example, hydrogen's going to be positive. Just as you see on the left, we have to go ahead and point all of our vectors from the positive atom to the negative atom. So if every single vector is pointing in, there's no way that those can cancel out, and so it has to be polar. The molecule is going to be 100% a polar molecule if your vectors are pointing in. However, if your vectors are pointing out, you really need to look at the geometry and see if that movement's occurring, such as a tug-of-war that was referred to earlier. This could be difficult at first, but as long as you take the time to actually go get a model, it should greatly help you out. So to finish up, let's actually write out polar bonds, yes or no, and polar molecule, yes or no. And you have enough information to go about and figure out if you have polar bonds for any Lewis structure in geometry and whether or not you would overall have a polar molecule. And so there you have it.